Okay, class. Today, our objective is we're going to define continuous functions mathematically using the definition. Okay, so today we're going to talk about what are the conditions that you need to meet mathematically in order to determine if functions are continuous. So the question is, what is continuous? Well, that is just simply saying there is no gap or break in your functions. Okay? So here's the definition of continuous function. The definition says here that for any function to be continuous, it must meet three given criteria. Okay? The three criteria are: one, the limit as x approaches the constant. So that constant is where you got to see if it's continuous or not, okay, of the function exists. This means that the limit as x approaches the constant from the left is equal to the limit as x approaches the constant from the right. So if the left and the right approaches the same output at C, wherever the domain is, the constant is for the domain, then the limit exists. Okay? Condition 2 says in order for it to be continuous, not only does the limit have to exist at C, when you plug in C into your function, it has to also exist. That means there's a value that it's equal to, the output equal to some value. Okay? And then finally, not only the condition 1 and 2 have to be true, they also have to equal each other. In other words, the limits that you got from condition 1 has to equal to the value of C that you plug into your function that you found in 2. And so they have to equal to each other. So this is the mathematical definition using limits of a function to define whether a function or any function is continuous at a given value C on the number line. And so I'll show you what it means with some examples so that you can clearly see what I'm talking about here. Okay? Here's example 1. There we go. Take a look at example 1 here. You can clearly see at example 1 here that the limit as x approaches C from the left is here, right there. The limit as x approaches C from the right is right here. So you can clearly see the two limit does not equal each other. There's a gap between them. Okay, so in this case, the limit of f of x does not exist. That means condition 1 fails. Okay, that's why this function is not continuous. Look at the next example. Here, the limit as x approaches C from the left, right here, and the limit as x approaches C from the right, right there, approaches the same value. So condition 1 is good to go. But take a look at here. If I plug in C into my function, so I take C here, I plug into my function here, it's empty. You guys see that? It's empty here. So that means condition 2 fails. And so this function is not continuous because f of C does not exist. So we go back. Condition 1, good to go. Condition 2, fails. Okay? Let's take a look at the third case. Here's the third case. Okay? Take a look at the third case on the left. You see here? Take a look at here. You see that the limit as x approaches C from the left, the limit as x approaches C from the right, see the left, the right, that approaches the same value. If I plug a C into my function, I have a value that is way up here. It doesn't fill this gap. You see that? So in this case, condition 3 fails. So 1, check. 2, check. But condition 3 fails. And therefore the function is not continuous because by the mathematical definition, the limit does not equal the actual solid point. See, the value has to equal the limit in order for it to be continuous. Now, take a look at the third case. This is called a continuous function because you take a look at the c value here. When I plug it here, is right about here. See that? The limit as x approaches c from the left, the limit as x approaches c from the right, they all approaches the same value, which is 2. You see that? If I plug c into my function, guess what? There's no other point except that point right there. So it's also the limit itself. So you can see here, condition 1 is met, condition 2 is met, and condition 3, the limit as x approaches c is equal to f of c as well. So condition 3 is also met. And this is considered a continuous function at c. Okay? So now that you understand a little bit about continuous function, I'm going to show you some examples where a function might not be continuous. Okay? And so you can see the different type of functions that could create a discontinuity in your function. All right? So now let's take a look at some examples of that. There we go. Here's example 1 and 2. Okay? The first case of discontinuity, where it's not continuous, is called a removable discontinuity. So here's removable discontinuity. What does it look like on the graph? You see here? Here's my function. I have a function that is quadratic divided by a function that is not quadratic. If I simplify this by using the Xbox method, I would get this 2-factor, x plus 2 and x plus 1. And you can see we know that x cannot equal negative 2, because if it does, negative 2 plus 2 is equal to 0. You cannot divide by 0. It's undefined. So that's why there's an empty spot here. Now notice here, it's undefined here, but take a look. You see how we can reduce? So when we can reduce out like this, it creates a little tiny hole or gap in our function. Okay? And if this gap is not filled by a solid point, then you can see it's undefined as c. You see here? It's undefined. Because if I plug in c here, what do I get? Nothing, an empty spot. And that's called a removable discontinuity. One little tiny gap. Okay? Take a look at the other case. You look at here. Notice here, we have the limit from the left and the right. See, here's the left, here's the right. It approaches negative 1. Okay? The value, though, notice here, you take a look at it, the value, on the other hand, is negative 2. See? F of c is right here. When I plug in my constant here, I get this solid point. And this doesn't fill the little gap. Again, the limit does not equal the actual value. So you can see here, and look at this case, that condition 3 fails. And therefore this is also discontinuous. And these types of discontinuity, when there's a little tiny hole, are called removable discontinuity. Okay? Let's look at another type. There we go. These two types are called the infinite and the jump, and that will conclude the 3 basic discontinuity that we're going to talk about. Okay, we'll talk about more advanced one at a later date. There's 2 more that we will talk about, but for the purpose of this lesson, I'm only going to talk about removable, infinite, and jump. So let's examine infinite. Okay, take a look at here. Notice x plus 4 divided by x minus 1 and x plus 8. This is fully simplified, but we cannot reduce because they don't have any terms that are the same. So unlike the previous one, where these two are the same and we can reduce, these are called removable. If you look at this one here, you cannot reduce them. See that? So we know that x cannot be 1 because 1 minus 1 is 0. X cannot be negative 8 because negative 8 plus 8 is 0. And when you divide by 0, it's undefined. And so when you cannot reduce, it creates what's called a vertical asymptotes, which you guys have talked about it in pre-calculus. Okay, here's vertical asymptotes there. That means you can never cross those lines because those values are undefined at positive 1 and negative 8. They'll be undefined. In other words, my function will approach infinity or negative infinity or infinity as you get closer and closer to those dotted lines. In those cases, they're called infinite discontinuity because when you have those values, those x values, okay, it becomes undefined. You divide by 0. And those are called vertical asymptotes. We'll talk about it at a later date, okay? Just know that when you have something in the bottom that's undefined, when you plug a value in is equal to 0, and you cannot reduce, then that's create what's called infinite discontinuity. Okay? If you can reduce like this, then those are called removable discontinuity. Okay? The third case is called the chump discontinuity. So notice here, you look at the limit from the left, it's approach about 1. And you look at the limit from the right, it approaches about 5. So clearly the limit from the left does not equal to the limit as x approaches c from the right. So this one fails condition 1 because the limit don't exist. And this is often called a chump, and the reason why we call it chump, because notice here, you at the bottom here, you jump from 1 all the way to 5. And this is called a chump discontinuity. And those kind of function will look like this. You have more than one type of function combined together. They're called piecewise function. Okay? Piecewise, piecewise function, because you have piece by piece function put together. And that sometimes creates what's called a chump discontinuity because there's a gap between the limit from the left and the limit from the right, and therefore it fails condition 1. Okay, so those are the 3 types of discontinuity. Let's review them quickly. They are removable discontinuity, where you can reduce the top and the bottom, so we know it cannot be negative 2 because they'll make this 0 down here, but we can reduce another factor that's the same on top. Okay, or in this case where you have the same condition here, but you have a point f of c, when you plug in c to your function, does not close the gap of your limits, and therefore you fail condition 3, and those are called removable discontinuity. Then you have what's called the infinite case, where you cannot have a denominator that is equal to 0. So in this case, x cannot be 1 or negative 8, and therefore it's undefined, so you have infinite many vertical asymptotes that you cannot cross. Okay? And then the third case is called the chump, where you have a bunch of functions mixed together, and sometimes the limit from the left and the right jump from one location to the next at a certain domain x values of 1. As x approaches 1, it jumps from the left of 1 to the right of 5, and that's called a chump discontinuity, and often called piecewise function. Okay, so aside from those 3 cases, everywhere else it should be continuous. Okay, get that? Now we're going to practice with some examples using the definition so you can see exactly what it's looked like mathematically. Okay? Continue to part 2.